Good morning, and this is lecture number 3 in kinetic theory of gases. And I hope you remember what we had done in the previous class. In the previous class, we had discussed the different types of speeds: RMS speed, most probable speed, average speed, speed of sound. We had also seen which is um, which speed is highest, which speed is lowest, and we had also seen their ascending or descending order. We had also seen on what all factors RMS speed of gas molecules depends on. RMS speed of a gas molecules is root over 3RT by the molecular weight. Yes or no? It only depends on the absolute temperature. Remember, the temperature has to be on absolute scale. It depends on the temperature and temperature alone. It does not depend on pressure, because you can change the pressure in such a way that density also changes and the ratio of P and rho remains constant. Then temperature will remain constant. So when we talk about VRMS, we never say that it depends on pressure. We never say that it depends on density. We only say that it depends on temperature. We understand this, yes or no?
So,
We had also seen that it is for different gases. RMS speed is inversely proportional to its root of its molecular weight in kgs. Remember, this molecular weight has to be put in kgs. The heavier the gas, the less is the RMS speed going to be. We had also discussed things about the total kinetic energy of the gas molecules, and I had given you a note. Yes or no?
yes, sir.
The note is still there with me, and the note looks like this. Total translational kinetic energy per mole is 3/2 RT. Do we remember this?
Yes, sir.
The total kinetic energy, translational kinetic energy becomes 3/2 nRT. Translational kinetic energy per molecule becomes 3/2 kT, and total translational kinetic energy becomes 3/2 nKT, where n stands for the number of molecules of the gas, capital N stands for the number of moles of the gas. And we have seen that if we have equal moles of gases, no matter it is oxygen or nitrogen or hydrogen, at same temperature they will have the same transitional kinetic energy. Yes or no?
Yes, sir.
But we had also seen some transitional kinetic energy per gram. Per gram, it depends on the molecular mass of the gas. Do we understand this? Do we remember this? I had given you everything point wise. Yes or no? Okay. That was it for the last class, and you will find that majority of question comes from in this topic comes from this kinetic energy wala principle. We'll go again more into this kinetic energy wala principle in today's class, which we will be winding up. Today's class, as I guess you must be knowing, what are we going to discuss in today's class? Are?
Degrees of
What are we going to discuss in today's class?
degrees of freedom.
Degrees of freedom. And this degrees of freedom is going to give us more insight into this kinetic energy of gases, and probably you will be able to make more sense of this transitional kinetic energy. So without much ado, we'll move on to this degrees of freedom, denoted by the small letter f. Oops, what's happening here? This thing has happened here. Small letter f. What is this degrees of freedom? Now, you can define this degree of freedom in two ways. You may not have to write this definition. You can just read it from your note. The number of independent ways in which a molecule or an atom can exhibit motion. If I have a point object, how many different ways it can move? It can move along x-axis, it can move along y-axis, it can move along z-axis. So it will have 3 degrees of freedom. The number of independent ways in which a molecule or an atom can move, can exhibit motion, or the number of independent coordinates that are required to specify its position, or the state of that system, how many coordinates are required. For example, if you have a point object, it is moving in space, you will need 3 coordinates to specify its position: x-axis, y-axis, and z-axis, and therefore it has 3 degrees of freedom. Number of independent coordinates, or the number of independent ways in which a molecule can exhibit motion, is known as degrees of freedom, denoted by the letter F. Do we understand this?
Oh,
Well done.
yes, sir.
Good. Now, these degrees of freedom, this is what you need to understand, can be classified into 3 different types. One is known as translational degree of freedom. Translational degree of freedom comes from translational motion. Translational motion means that the body is moving as one system, as one body. I will not go much into translational system. A car moving on road is a translational motion. It is not rotational. This fan, which is on the top of my head and your head, what type of motion this fan is having? The fan that I can see.
Motion.
Which one?
Translational motion.
That is having translational motion. Are you in your senses? Or you have lost all the senses? The motion that the fan is having is rotational motion, beta. You don't know this? That is not translational, that is rotational motion. Do we understand this? Yes or no? Car moving on road, bus moving on road, not moving like this. Bus moving on road. Something moving on a circular path, a bike moving on a circular path, that is not rotational motion. That is translational motion. A fan moving like what it is moving on your head, that is rotational motion. The motion that the fan is having is pure rotational. Now think about a cycle or a bike ka tire. The bike ka tire or cycle ka tire, it is rotating as well as it is moving forward. Yes or no?
Yes, sir.
That is a combined motion. When I say combined motion, it is a combination of 2 motion. What are the 2 motion of which it is combined? The motion of a cycle tire when the cycle is moving on road, or a bike tire when the bike is moving on road, or a car tire when the car is moving on road. The motion of the car is transitional, but I am talking about the motion of the wheel of the car. What type of motion the wheel of the car has? Yes?
Rotatory motion.
What motion?
Rotatory motion.
No!
Rotational motion.
It is a combination of rotation and translation. The wheel is rotating, but at the same time, the wheel is going forward. So it is a combination of rotation and translation. Do we understand this? In short, you can call that motion of the wheel as pure rolling. Have you heard about this term, pure rolling? This pure rolling is a mixture of translational and rotational. Do we understand this?
Yes, sir.
So, that was all about motion. Similar to the motion of a wheel of a car, we can have motion of the molecules or atoms of the gas. Do we understand this?
Yes.
And this motion can be translation. If this motion is translation, it can have 3 degrees of freedom. 1 degree of freedom along x-axis, 1 degree of freedom along y-axis, and 1 degree of freedom along z-axis. Do we understand this?
Yes, sir.
So what are the maximum degrees of freedom in translational motion? What are the maximum degrees of freedom in translational motion?
3 degrees.
Who will write this? Will I write this or will you write this?
Wheel right, sir.
Then write, sir. 1 minute, sir.
Completed, sir.
Okay, have you done this? Okay. Just give me a minute. Okay. So the first degree of freedom that we had seen was translational. What would be the next? Tell me, what would be the next? What would be the next?
Rotational degree of freedom.
Yes, you have seen it from the sheet, but it's good that you have seen it. Rotational degree of freedom, this comes from rotational motion. Now, a body can rotate on x-axis, a body can rotate on y-axis, and the body can rotate on z-axis. So how many maximum degrees of rotational freedom it can have? Tell me, how many maximum rotational degrees of freedom it can have?
3 degrees.
Maximum it can have 3 degrees of rotational freedom. Do we understand this?
Yes, sir.
If you understand this, sir, then we have the third type of degree of freedom. This is only for a gas molecule that we are talking about, and that is vibrational. This gas molecule can start to vibrate. Do we understand this? It can start to vibrate in its own position. Do we understand this?
No.
What are the maximum vibrational degrees of freedom? And this only occurs at very high temperature. If you start increasing the temperature of the gas at very high temperature, the molecules will start to vibrate. And the maximum degrees of freedom for vibrational motion is how many? 6, sir. It is 6, sir. Remember that, sir, and note it down, sir, because you will have to understand it, sir. Note it down, sir.
Done, sir.
Done, sir. Just give me 1 minute, sir. Now we will have this table, that the table is already there with you, and we will write and draw this table. And what does this table tell us? What does this table tell us? This is talking about the degrees of freedom for different types of gases. Monatomic gas, the gas which has only one atom in its molecule. These are basically ideal gases. Do we understand this? Helium, neon, argon, krypton, xenon, radon, whatever.
Yes, sir.
They only have translational degrees of freedom. They do not have rotational degrees of freedom. Why they do not have rotational degrees of freedom? Because it is a single atom. A single atom cannot rotate. Do we understand this?
Yes,
A
sir.
single atom is like a point mass. A point mass cannot rotate. A point mass can only translate. Do we understand this? They also do not have any vibrational mode. So the total degrees of freedom are only 3, and they are purely translational. Do we understand this?
Yes, sir.
One is along x-axis, the other one is along y-axis, and the third one is along z-axis. Are you going to draw this diagram or not, or see my face?
Sir.
Please draw this table, bacha. Please draw this table so that we can move ahead in life. We can move ahead in life. That's the only thing that we got to do, bacha. That we keep on moving ahead in our lives. And you have a minute to win this. I hope you are winning it. You'll have to draw this, and then I will give you more gyan on this. And if you understand this gyan, you will have a very good beginning of your dynamics. 1 minute, minute to win it. Have you noted it down, bacha? Yes, sir. Then, sir, the second type of gas, sir, is diatomic gas, sir. H2, O2, N2, Cl2, F2, Br2, whatever. They have 2 atoms in their molecules. Do we understand this?
Sir.
What are the degrees of freedom that they can have? They can have 3 degrees of translational freedom. One along x-axis, one along y-axis, one along z-axis. Do we understand this?
Yes, sir.
They can also rotate. Now, look here and try to make sense. Let us say that this is a diatomic gas ka molecule. I have one atom here and I have one atom here. Do we understand this? One atom here, one atom here. Do we understand this?
No.
Now this gas molecule can rotate in different ways. It can rotate along this axis, so it will rotate like this. Dhar, gar, 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 gar. Do we understand this? It can rotate along this axis. If we rotate along this axis, it will rotate like this. If it rotates along this axis, it will rotate like this. So these are the 2 degrees of freedom it can have. Now, if it wants to rotate along this axis, all the 2 atoms are here. So its moment of inertia is 0 along this axis. So it cannot rotate along this axis. Do we understand this? If we rotate like this, the moment of inertia is 0. Do we understand this? Yes, sir, or no, sir?
Yes, sir.
Therefore, bacha, the degrees of freedom that this gentleman will have of rotation are only 2. It does not have 3 degrees of rotational freedom. Do we understand this?
Sir.
Because the molecule is linear, as you can say, the molecule is linear. Along one axis, the moment of inertia is 0. Do we understand this?
Yes, sir.
It will not have any degrees of freedom in vibration because at high temperature it does not vibrate. So the total degrees of freedom become 5. Do you understand this?
Yeah.
This is what you will write. And I'll give you a minute to win it.
Done, sir.
Answer. Then what is the third type of gas that we will have? Triatomic or polyatomic gases. Now these triatomic or polyatomic gases can be of 2 categories. One is linear in a straight line, or one is triangular, which is non-linear. The example for linear triatomic gases are CO2 and C2H2, which is polyatomic. Do you understand this? The structure is linear. Do you understand this? They will have 3 degrees of translational freedom and 2 degrees of rotational freedom. Why not 3 degrees? Because along one axis it is 0. Do we understand this?
Yes, sir.
At high temperature, they will start to vibrate. So they will have 2 degrees of vibrational freedom. Therefore, the number of degrees of freedom becomes 7. 1 along X, 1 along Y, 1 along Z, 1 of rotation along Y, 1 of rotation along Z. Because along x-axis they cannot rotate, moment of inertia is 0 and 2 degrees of vibrational freedom. Have you written this? You'll have to write this. But before writing this, you also write the degrees of freedom for triangular gases. 3 degrees of translational freedom, x, y, z. We understand this. Now the rotational degrees of freedom are 3. Do we understand this now?
Yes, sir.
Because if the gas is triangular, it can rotate all on 3 axes. Therefore, the total number of degrees of freedom becomes 6, 6, 6, 6, 6, 6, 6, and I'll give you a minute to win it. Note it down. Have you written this?
Sir.
Yes, sir. Then, sir, next thing, sir, is this, sir. Maxwell's law of equipartition of energy. I hope you can see this. This is what is given by Maxwell, and he says that if you talk about gas molecules, energy associated with each degree of freedom. So you can think of this gas as a father, and this father has a lot of money, wealth. The wealth of the gas is energy. Energy is the wealth of the gas. So what is this gas going to do? This gas is going to equally divide this wealth, equally divide this energy amongst all the degrees of freedom. Do we understand this?
Yes, sir.
Every degree of freedom will get equal energy. And if I talk about every degree of freedom per degree of freedom per mole, so I will write it like this: energy per degree of freedom per molecule. Do we understand this?
Yes, sir.
Total energy or energy per degree per molecule of any gas atom would be half kT. This is the most important thing that you must remember. Will you remember this?
Yes, sir.
If the number of degrees of the freedom is F, total kinetic energy of the molecule will be multiplied by F, and it will become half F kT. Do we understand this? Yes or no?
Yes, sir.
I will try to make more sense. Let's see how I am going to make more sense out of this. I hope you have written that thing that I had shown you. You have written Maxwell law of equipartition of energy. Yes or no?
Minute, sir.
Written that? So basically, I'll try to elaborate now. What does Maxwell law says? Energy per degree of freedom per molecule will be equal to half kT. Do we understand statement number one?
Yes, sir.
Now, if I write it as point number two, energy per molecule, so I will divide it by the number of degrees of freedom. Do we understand this?
Yes, sir.
Energy per molecule will become half of FKT. Do we understand this?
Yes, sir.
Then if I have to find the total energy of gas, I will multiply it by the number of molecules of the gas, and now the answer becomes half N F K T, where N stands for the total number of molecules of the gas. Am I being clear? Do we understand this?
Yes, sir.
Who will write this, sir? You will have to write this, but before writing this, I will add three more things here. So we'll write all the six things together. Point number four. Now, when I'm talking about this, I must also talk about this energy per degree of freedom per mole. Now I have changed the molecule to mole. Can you now tell me what would be the answer? I've already told you what comes with mole and what comes with molecule. Can you tell me what will be the answer of energy per degree per mole? When I'm talking about energy, I'm talking about the internal energy of the gas. Can you tell me when I talk about this energy, this is the internal energy of the gas? Yes or no? Do we understand this?
Yes, sir.
If I talk about energy per degree per molecule, I use half kT. If I will talk about energy per degree per mole, what will be the formula? I'll give you 1 minute. Tell me.
Half FRT.
Arey, don't put F. It is per degree, so it will be half RT. Do we understand this? Yes or no? Now when I write it as energy per mole of a gas, per mole, the energy will be multiplied by F. So it will become half FRT. Am I making sense? Yes or no?
Sir.
Then if I write the total energy of the gas, total internal energy of the gas, the formula will become half N F R T. Where what does this N stand for? What does this N stand for? What does this N stand for?
Number of moles.
Number of moles. That is absolutely correct. What about this N? It stands for.
Number of molecules.
That is correct, my dear friends. Now you will get 1 minute to show your talents. By showing your talent, what I mean is that you will write it. A minute to minute. Have you noted it down, bacha?
Done, sir.
Done, sir. Then, sir, this thing, sir, which is taken from your notes, sir. Same thing explained here. Energy related with each degree of freedom per mole they are talking about. Do we understand this? Per mole, that will be half RT. Do we understand this? Energy related with all degrees of freedom per mole will be multiplied by F, FRT by 2. Do we understand this?
Yes, sir.
If I multiply it by capital N, this becomes the total internal energy of the gas. Yes or no? From here, you can find out the value of Cp and Cv. Will not go further than this. You have to remember the relation between Cp and Cv. Do we understand this relation? Cp is Cv plus R. Have you seen this relation? Cp is Cv plus R. Yes or no?
No.
Yes, sir. Then you will remember it more, sir. And you will remember the other relation as well. I will do what? Will increase the size of this gentleman and bring it on the full screen, and you will note down these things very, very carefully. My CV is F by 2R. Yes or no?
Yes, sir.
My F. There is a relation between F and gamma also. What is the relation between F and gamma? You can see the relation here. You can see the relation here between gamma and F. Yes or no?
Yes, sir.
From here, you can find out the relation between F and gamma also. F will be equal to 2 upon gamma minus 1. Yes or no? So this is equation number 1, the value of CV. CV is F by 2R, या R upon gamma minus 1. Equation number 2, CP is CV plus R, so it becomes F by 2 plus 1R, or it becomes gamma times R upon gamma minus 1. the value of gamma, which is the ratio specific heat, it is Cp by Cv. It also becomes 1 plus 2 by F, and the value of gamma becomes 1 plus 2 by F, or the value of F becomes 2 upon gamma minus 1. Can you remember these relations for me? Yes or no? They speak up.
Yes, sir.
You have to remember this relation, note down this relation, and remember it. Do not forget it. I will give you a minute to note it down. Have you noted it down, bacha?
Yes, sir.
Yes, sir. Then, sir, this thing, sir. By putting the values, you can find out. F is 3 for monatomic, 5 for diatomic, for triatomic linear it is 7, and triatomic non-linear it is 6. Do we know this? Yes or no?
Yes, sir.
From there, you can find out the value of Cp, Cv, and gamma for each of the gases, and you cannot forget these values ever in your life. So this is how you will identify which gas is which. For example, if gamma is given as 5 by 3, it is monatomic gas. Do we understand this?
Yes.
And the Cp will be 3 by 2R and Cp will be 5 by 2R. All these things have to be memorized. Draw the table. Your time starts now. Have we drawn this table? Yes or no? No or yes? I think you have not drawn it. I'll give you a minute.
Done, sir.
Have you written this? Yes or no?
Yes, sir.
Well done, sir. Then, sir, the important points about this question will be coming based on these important points. Point number one: when atomicity increases, degree of freedom increases, but value of gamma decreases. Yes or no? Monatomic gas, the value of F degrees of freedom is less, but gamma is maximum. For monatomic gas, the value of gamma is maximum. You will have to remember this. Internal energy Cp, Cv, and gamma is same for all gas mixtures if the atomicity of the gas is same. If we have a mixture of monatomic gases, gamma, Cp, and Cv will be same for all. Yes or no?
Sir.
If we have a gas mixture with different atomicities, we have one monatomic gas, one diatomic gas, polyatomic gas, then for the gas mixture, gamma will change according to the following condition. For diatomic gas, gamma will be less than the mixture. It will be less than the gamma of monoatomic gas. Do we understand this? That means the atomicity or the atomicity of the mixture will lie between monoatomic and diatomic. Do we understand this? A minute to win it, a minute to write it. Note it down. Have you noted it down, bacha? Yes, sir. Then, sir, this thing, sir, Maxwell law of equipartition of energy. We have already seen that. Energy per degree per mole is half kT. Yes, or energy per degree per molecule is half kT. Do we know this? Yes or no? Yes, sir. Then, sir, these special points about this Maxwell law of equipartition of energy. Same thing that we had discussed. Same thing that we have discussed is given here, and you will note it down as it is. Point number one, if you have any doubt, please tell me. Point number one. Point number one. Point number one. What is point number one here? At 0 Kelvin, degrees of freedom is 0. Gas cannot have any energy. Do we understand this?
Yes, sir.
At T Kelvin, energy per molecule per degree of freedom. They have not written per molecule. Per molecule per degree of freedom is half kT. Yes or no? If F is the degree of freedom, total energy of each molecule is F by 2 kT. Yes or no? Total energy per mole is F by 2 RT. Yes or no?
Yes, sir.
For capital N moles of the gas, it will become capital N FRT by 2. Yes or no?
Sir.
Now you can write it as NCV because F by 2R is CV. Yes or no?
Sir.
So you can write the internal energy of gas is NCV into T. Yes or no?
Sir.
Similarly, you can write the change in internal energy. Oops, what has happened here? This thing has displaced. Similarly, you can write the change in internal energy. When the internal energy changes, you can write that the change in internal energy is N into CV into delta T, where delta T is the change in temperature. Do we understand this?
Yes.
This change is path या process independent. That means if I change the state of the gas in any process, one thing always remains constant, and that is the change in the internal energy. Do we understand this?
Yes, sir.
Change in internal energy only depends on N, number of moles, 2 CV, which is constant for a gas, and delta T, which is the change in temperature. So no matter how you change it, the change in internal energy is process independent. Do we understand this?
Sir.
You will have to write this and remember this. I'll give you a minute to win it.
Done, sir.
Done, sir? Then, sir, these things are Maxwell's law of distribution of velocities. You may not draw this diagram, but you will have to understand the important points of this diagram, which you can note in your sheet only. So you can note whatever I'm babbling in your sheet, and this is what you need to understand. What do you need to understand? This is what you need to understand. Do you see the diagram on the this? Yes or no? Are, do you see the diagram?
Sir.
What is the important thing that you have to understand? See, the temperature here is 500 Kelvin. Then the temperature becomes 1000 Kelvin and the temperature becomes 2000 Kelvin. So temperature is increasing, yes or no?
No.
When the temperature is increasing, you can see VMP. VMP means most probable speed, yes or no? When
No.
temperature increases, the most probable speed also increases, yes or no?
No.
But the number of molecules which are having this most probable speed, the number of molecules which are having this most probable speed, the number of molecules which are having this most probable speed, that decreases. Yes or no? Do we understand this?
Yes, sir.
This is what you got to remember. I'll give you a minute to note down this thing on your sheet. Have you noted it down, bacha?
Yes, sir.
Then these points again, you may not write these points. You will mark it in your sheet because you will not have so much time to write these points. Every point is a potential question. Do we understand this?
Yes, sir.
Point number one, at any given temperature, a graph can be drawn between the speed and the number of molecules. This is known as the velocity distribution curve, VDC. Number two, the velocities of molecules of a gas are in between 0 to infinity. So the gas molecules can have any velocity from 0 to infinity. Do we understand this?
Yes, sir.
Out of this, we have seen some velocities. One is known as V average, one is known as VMP, and the other one is known as VRMS. Yes or no? Yes or no?
Yes, sir.
With the increase in the temperature, the most probable velocity and the maximum molecular velocity increases. Yes or no? The number of molecules within certain velocity range is constant throughout the velocity. Oh, you can leave this point. And this may not come. The last point is important. The area enclosed between NV, number of moles, number of molecules, and velocity curve, and the velocity axis gives the total number of molecules. I have underlined this. What it actually means is, I will show it on the graph so that it makes more sense. What it means is this. 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 Have you seen what we had underlined? Yes or no?
Yes, sir.
Now see what it means. It means that if I find the area, the red area is the area between the graph and the velocity axis. Do you see this red area at 500 Kelvin? Do you see this red area which I have drawn under 500 Kelvin wala curve? Yes or no?
Oh.
This red area, which is the area of the curve at 500 Kelvin, this will give me the total number of molecules of the gas at 500 Kelvin. Do we understand this?
Yes, sir.
That is the most difficult question that can ever come, whether it's your exam or JEE or JEE Advanced. This is the most difficult question that can come, and I have given you that formula and that understanding. I hope this makes the point absolutely clear. Do we understand this? Can I move ahead in life?
Yes.
Have you have you have you done the same thing in your sheet? Yes or no? Yes, sir. No, sir. Then, sir. Better, sir. I go, sir. And this is the definition of mean free path of gas molecules. This definition will come as a question in your exam, and I hope I have told you this definition. If I have not told you this definition, this is the time where I'm going to tell you What is the mean free path of a gas molecule? What is the mean free path of a gas molecule? Gas molecules are in constant motion. When they are in constant motion, they are going to collide. Now, in between two collisions, in between two consecutive collisions, they travel some distance, and that distance is known as the mean free path. Do we understand this? That distance is known as the free path. If I find the average distance, because a molecule will not have one collision, it will have almost infinite collisions. If I find the mean of all those, that is known as the mean free path. So between one collision, the distance is free path. If I take the average of all the collisions, the distance is known as mean free path. Do we understand this? Can I have some raise hand? Do you understand this? You will have to write this because this is a potential question. I'll give you a minute, 2 minutes. Have you noted it down, bacha? Okay. If you noted it down, this is the value of this mean free path. Lambda m is known as the mean free path, and these are the different ways in which you can write this. 1 by root over pi d square n, m by root over pi d square mn. These are different ways in which you can write it. Remember, the more the number of ways you can remember, it is better for you. I will not explain all these. There are different formulas. D stands for the diameter of the molecule. N stands for, small n stands for molecular density, total number of molecules divided by V. We have written total number of molecules as N. Small n here, it is small n is small n under small n stands for molecules per unit volume, so that is different. Please remember this. Rho is known as the density of the gas, and P is the pressure, V is the volume. Capital N here is the number of molecules. So do we understand? This capital N here is our small n, and this small n is small n divided by V. Do we understand this? These hands? Okay. These are the different ways in which you write this. This is way number 1. This is way number 2. This is way number 3. And this is way number 4. Any way can come as a question. Please note it down.
Done, sir.
Have you noted it down, bacha? Okay. Now we'll move on to some questions. Whatever part is remaining, I will tell you, and you will read it on your own. Can you do that for me?
Yes, sir.
So whatever part is remaining, there is nothing that I can explain there. So I will ask you to read it on your own, and I hope you will not let me down. I will take this time to do some questions here. Okay? And this is the first question that comes to you. If F is the total degrees of freedom of the molecules of the gas and the ratio of specific heat Cp by Cv, the value of gamma, how much is the value of gamma? Do we have any idea? Which one? One, two, three, four. What is the answer? A, B, C, D. What is the answer? What is the value of gamma? F. F is the number of degrees of freedom. What is the value of gamma? They are asking. You don't know this? And the answer is 3. Yes. 1 plus 2 by F. I've already told you this. No prizes for guessing this one. I will move my attention to the next question. And this is the next question. Let's see who does this. The temperature of an ideal gas is kept same during expansion. You're expanding the gas, temperature is constant, gas is doing some work, obviously. We'll come to this work in the next class. The internal energy of the gas during the process, A, B, C, D. And the answer is it C, it remains same. Why does it remain same? Tell me the answer also. Tell me the reason also. Arey, tell me the reason also.
Energy does not depend on temperature.
Huh? Internal energy depends on temperature. Temperature is constant. So the internal energy will be constant. Do we understand this?
Yes, sir.
Okay. Let's see if you can tell me this one. 83. Oh, I think you have done this. 3 by 2 RT, 3 by 2 KT. That is the correct answer. Well done. Well done. Have you solved this exercise on your own before that? Very good. Very good. That is absolutely brilliant. Absolutely brilliant. And this one. This one comes in line. Question number 88. Oops, 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 oops. You can see only half of this question. That's very bad of me. I hope you can see this now. Statement Cp minus Cv is R and gamma is Cp by Cv, which is 1.67. A and B are true for all gases. A is true for all ideal gases, but B is true only for monatomic gas. That is the correct answer. Good one. So this is good. I am very impressed. I come to this one. I come to this one. Come to this one. 96. If the ratio of specific heat is gamma and R is the gas constant, and what will be the value of specific heat at constant volume? He is asking about CV, not CP. CV is asking you the value of CV, 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 CV. And the answer is number 1, R upon gamma minus 1. That is correct. No prizes for guessing this one. Now comes this one. Now comes this one. Question number 91. Question number 91. The energy of a monatomic gas is pure rotational, pure translational, and the answer is pure translational. That is correct. That is correct. If we remember all these things, life is going to be a cakewalk. This is the next one, 101. The kinetic energy associated per degree for freedom of a molecule, and the answer is kinetic energy per degree of molecule per degree of freedom for a molecule. How much kinetic energy it has for 1 degree for one molecule, and the answer is per degree per molecule. How much is the energy? There is no potential energy. The only energy is kinetic energy, and the answer is Maxwell distribution law. Energy per degree per molecule is half kT. Do we understand this? Arey, tell me yes, tell me no.
No.
This one. 111. Nelson. Britishers are very afraid of Nelson. There was an umpire known as Dickie Bird. You might not have heard his name. And when England used to be on 1-1-1 in a match of cricket, and when they always used to somehow lose wickets. So when this 1-1-1 was crossed and they reached 1-1-2, umpire Dickie Bird used to hop. 1-1-1. Nelson. What is the answer for this, Nelson? Gamma is 1.4. Which type of gas this is? Monatomic, diatomic, or triatomic? That is the first question. Then if it's monatomic, then the answer would be one of the two. And the answer is 1-1-1, Nelson. Answer is 3. It's a diatomic gas. Well done. Well done. That means we have drawn the diagram, drawn all these things correctly, and you can see the same question comes in variety of ways. And if you remember simple things, here comes simple question. 1-1-1-6. 1-1-6. Which of the following formula is wrong? And the question and answer is pretty straightforward. What is the answer, bacha? Arey? So much time? And the answer is 4. 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 Then this one. Let's see what is the answer for this one. 125. 125. The specific heat of an ideal gas depends on temperature. A, B, C, D. Does it depend on temperature? Answer is 4. It does not depend on temperature. That is correct. That is absolutely correct. Then this one, and this is only for your knowledge. If this question repeats, it is +4 for you. Kinetic theory of gas was given by which scientist? You must know this name. Your question comes directly. Which one? If I have not told you, it was given by Bernoulli. Answer is B. Remember it. Do not forget it for your entire life. And comes this one. I'm trying to cover as many questions, taking into account all types of questions that have come. According to kinetic theory of gases, the relation between internal energy U and the absolute temperature is which one? A, B, C, D. A, B, C, D. What is the answer? And the answer is 2. It depends directly on the temperature. U, internal energy, is directly proportional to temperature. I hope you understand this. This is the next one. Average kinetic energy of a gas molecule depends on volume, molecular mass, absolute temperature, mass of the gas. Which one? 133. And answer is 3. Absolute temperature. Yes, we do understand this. We do understand this. We do understand this. Let me see if I have. This one. A question might be put in this fashion. 149. Correct relation between molar specific heat at constant pressure and constant volume. Now, this might look a bit confusing. Again, such questions, they will have to tell you what is Cp, what is Cv, what they mean by Cv. The correct relation is Cp minus Cv by R. But sometimes they give you in different units. Here it is given in different units, and therefore the answer is R by J, where J stands for that mechanical equivalent of heat. Do you understand this? So remember, such questions may come. Such questions may come, and in PMT, I have seen a lot of questions where theoretically or they have not given the question correctly, but they have asked and the answer is given. One last question, which is among the last of this chapter as well. I hope you can do the rest of this chapter, rest of the question. This is the last question from my side. 167. The degrees of freedom of a molecule of a triatomic gas. And the answer is 6. Yes, 3 degrees of translational freedom, 3 degrees of rotational freedom, and that is all that we have. Do we understand this? Yes or no? Now, what you got to do, the remainder of this chapter, which is basically about reading stuff, you will have to do on your own, starting from this point, the specific coefficient of a gas. 3 formulas are given. You will have to do all these 3 formulas. Can you do that for me? Read it. Remember the formula. Right? Then this table, if you can read this table and do this table on your own, I will be very happy. Don't worry, we will be doing this table in the next chapter. So even if you don't do this table, we will be covering it in the next chapter. Do we understand this? If you can write this, if you can draw this table now, after the class, it will be very, very helpful to all of us. Do we understand this? Then we have already discussed this. I had given you the van der Waals equation. You will have to remember this van der Waals equation. The real volume is V minus V and the pressure is A by V square. Do we understand this? You will have to remember this van der Waals equation for 1 mole of the gas. Please note it down. And van der Waals equation for n moles of the gas. A straightforward question will come here. Please remember this. Do we understand this? Can you do this for me? Yes or no? Yes, sir. Then you have these experiments which I've never seen come ever, but there can be a question from the MAGH experiment. You just have to remember all these conclusions. When you get time, you can go through this. I've never seen a question coming from this, but this is a part of your syllabus, and that is why I am showing it to you. Again, Dr. Andrews experiment, which is for an isothermal curve. We will do this isothermal curve. This is an isothermal curve. This is the ideal behavior, but this is how the gases behave. The gases behave in a different way. Do we understand this? Don't have to understand this. Just remember this graph. Can you do that for me?
Yes, sir.
Then we have two things which is known as critical temperature. Critical temperature is the temperature below which a gas can be liquefied only by increase in pressure and above which no liquefaction is possible. This is critical temperature. Or straight away question can come on this. Do we understand this? Similar to critical temperature, we have critical pressure and critical volume. Minimum pressure required to liquefy is critical pressure. At critical pressure and critical temperature, the volume of gas is known as critical volume. Do you understand this? Don't have to understand this. You have to remember these. You have to remember these values. Yes or no? You will have to do it on your own. Can you do it for me?
Sir.
Then we have these relation between critical VC standing for critical volume, TC standing for critical temperature, and PC standing for critical pressure. You have to remember these relations. Can you remember these relations? I've now never seen these questions come, but this is a part of your syllabus. That is why you can you do this? Can you remember these relations? Do it if you get time. Results for a real gas. All real gases follow van der Waals equation at every possible temperature. Remember there was a question where they was asked at what temperature and pressure real gases obey van der Waals equation. Do we remember that question? That is the question coming from this point. At a given temperature, the volume and the pressure for real gas are very low compared to ideal gas. So question can come. If I compare an ideal gas and a real gas, what will be the volume and pressure? They are very low. For change in kinetic energy of a real gas is same as change in kinetic energy. As you can see here, for an ideal gas, it is NCV delta T. Here the value has changed, and that is the formula that it looks like. No one is going to ask you this formula. But if you just go through this once you go home, that would be better. Do we understand this?
Yes.
Well, on that note, I will wind off this class. This is done. We are done with your kinetic theory of gases. In the next class, we'll be starting with thermodynamics, a different process. So see you in the next class. Have a nice day. Take care. If you have any doubts, please ask.